to understand in detail the unit root stochastic process, its characteristics, and what is the reason behind it being called a unit root. Secondly, you will learn about the integrated stochastic process and its properties. You shall be able to identify the differences between the autoregressive model and the moving average model. And finally, the concept of spurious regression will be taught, which would mark the end of the module.
In this module, a class of nonlinear processes which have a root that is not constant but is stochastic and varying around unity is introduced. The process can be stationary for some periods and mildly explosive for others. Stochastic unit roots are seen to arise naturally in economic theory as well as in everyday macroeconomic applications. It is well established that many economic series contain dominant smooth components even after removal of simple deterministic trends. This is particularly true for series from finance and macroeconomics. A traditional way to model these components is as random walks, leading to integrated of order 1, I1, and autoregressive integrated moving average of order P, 1 and Q, that is ARIMA P1Q models in Box and Jenkins 1972 terminology. The success of such models with economic data and relationships between groups of such series, including the idea of cointegration, has resulted in a considerable literature and special statistical techniques to handle the problems of inference with data having this property. If a series is such that its first difference is stationary, then the series is said to have a unit root. It is quite possible that such roots occur in practice. However, there is a little economic theory that produces them, and in practice there are many types of processes that have near unit roots and are very difficult to distinguish from perfect unit root processes given a finite sample. The process of stochastic unit root processes are often markedly different from comparable properties of perfect unit root processes. Another characteristic of stochastic unit roots is that they are quite difficult to distinguish from perfect unit roots. It can be seen in applied economic literature on time series regression equations with an apparently high degree of fit as measured by the coefficient of multiple correlation R square or the corrected coefficient R bar square, but with an extremely low value for Durbin-Watson statistics.
Let us first understand the concept of unit root. Suppose we take a random walk model yt is equal to beta yt minus 1 plus ut. This model is the first order autoregressive model, that is, with a lag of one time period. If in this model the coefficient beta becomes equal to 1, the equation can be written as yt minus 1 is equal to ut. This means that the first difference between the endogenous variable yt is equal to the white noise term ut. The problem of unit root arises, which leads to non-stationarity problem in the series. Therefore, a unit root process is so called because the value of the estimator of first order autoregressive model becomes equal to 1. Now let's learn more about the unit root process through its features. The characteristics of a unit root process are: firstly, shocks to a unit root process are permanent in nature and would not be eliminated even if the series taken into consideration is converted into a stationary series. Secondly, a unit root process has a variance which moves towards infinity. And lastly, a unit root process can be converted into stationary by taking the difference. For example, if a series yt is integrated of order 1, then it can be integrated of order 0 with delta yt is equal to yt minus 1. Autoregressive moving average, that is ARMA model, when integrated of any order, say D, will become autoregressive integrated moving average, that is ARIMA model. So it becomes important to understand the meaning of integrated stochastic process. Let us start with a random walk process like yt is equal to yt minus 1 plus ut. As we all know from the previous modules that the error term ut is called white noise term, which is independently and identically distributed with zero mean and constant variance. It is mathematically expressed as ut is approximately equal to IID n, the function of 0 and sigma square, where ut, the white noise term, is approximately equal to IID, that is independently and identically distributed, n, that is the normal distribution. 0 represents the mean and sigma square represents the constant variance. Now let us go back to the random walk process expressed in the form of equation yt is equal to yt minus 1 plus ut. We take the first difference and we get yt minus 1 is equal to ut. This implies delta yt is equal to ut. In simple words, we can say that the first order difference is approximately equal to the white noise. That is, delta yt is approximately equal to the white noise term. Therefore, the series is said to be integrated of order 1 as the first difference is the white noise term. In general terms, any series is said to be integrated of order d if the dth difference is the white noise term. After studying the concept of integrated stochastic process, let us discuss its main properties. There are four basic properties. First, if xt is integrated of order 0, that is, xt approximately equal to I0, which is stationary, and yt is integrated of order 1, that is, yt approximately equal to I1, which is non-stationary, then their sum will be integrated of order 1 and will be a non-stationary time series. That is, xt plus yt is approximately equal to I1. Second, if xt is integrated of order d, then a function zt, which is equal to a plus bxt, will also be integrated of order d. The status of the series is not affected as far as integration is concerned by multiplying or adding of any constant to the series. The third property is if xt is integrated of order d1 and yt is integrated of order d2, where d1 is less than d2, then zt, which is equal to axt plus byt, will be approximately equal to id2. This implies that the series containing a combination of two time series will be integrated of the higher order amongst the two. And the last property is if xt is integrated of order d and yt is also integrated of order d, then the function zt equal to axt plus byt will be integrated of I d star, where d star can be equal to or less than d.
Autoregressive process. The notation ARP refers to the autoregressive model of order P. In general terms, we can define autoregressive processes as stochastic processes used to estimate the future values using the weighted sum of the past values. An autoregressive process assumes that the past values have an effect on the present values. The ARP model is written as yt is equal to beta 1 yt minus 1 plus beta 2 yt minus 2 plus beta 3 yt minus 3 so on plus beta p yt minus p plus mu t, where beta 1, beta 2 up to beta p are parameters and the random variable mu t is white noise. Some constants are necessary on the values of the parameters of this model in order that the model remains stationary. Moving average model is different from the autoregressive model in the sense that in the former, which is moving average model, the error term is regressed on the series, while in the latter case, the endogenous variable itself is regressed upon itself with a lag. Therefore, a moving average process is the sum of random shocks or error terms. The notation MAQ refers to the moving average model of order Q, which is written as yt is equal to mu t plus gamma 1 mu t minus 1 plus gamma 2 mu t minus 2 plus up to gamma q mu t minus q.
Now let us move on to the concept of autoregressive processes. These processes are the ones in which regression takes place on the lagged values of the endogenous variables itself. Let us take the example of the random walk model yt is equal to beta yt minus 1 plus ut. It includes one lagged value of the variable yt, that is yt minus 1. Thus, this is termed as autoregressive process of order 1 and is written as AR of order 1. The important point to note here is that if beta is equal to 1, then the series becomes a random walk process or a unit root process. Similarly, if our present value yt was based on two past values, that is yt minus 1 and yt minus 2, then it would be considered as an autoregressive process of order 2. Therefore, a series is generated by autoregressive process of order p if yt is equal to beta 1 yt minus 1 plus beta 2 yt minus 2 till beta p yt minus p plus ut, where beta 1, beta 2, beta p are the parameters and the random variable ut is the white noise. This series is denoted as AR of order p. In general, we define autoregressive processes as the stochastic processes used to estimate the future values using the weighted sum of the past values. Thus, this process assumes that the past values have an effect on the present values. A series is considered to be generated by a moving average process if the error term and its lagged values are regressed on the series. It can be defined as the equation yt is equal to ut plus gamma 1 ut minus 1 plus gamma 2 ut minus 2 till gamma q ut minus q. This is considered to be a moving average process of order q and is symbolically written as ma of order q. A point of difference needs to be noted between the autoregressive process and the moving average process is that in case of the former, the endogenous variable is regressed upon the series, while in case of the latter, the error term is regressed upon the series. Therefore, we can consider the moving average process to be the sum of random shocks or the error terms. After studying both autoregressive and moving average models, let us note the differences between the two. Firstly, autoregressive models are regressed on the lagged values of the endogenous variables, whereas the moving average models are regressed on the lagged values of the error terms. Secondly, the autoregressive models are stochastic in nature, that is, containing an error term, whereas the moving average models are deterministic in nature, that is, with no error terms.
In the statistical analysis of time series, autoregressive moving average models provide a parsimonious description of a weakly stationary stochastic process in terms of two polynomials, one for the autoregression and second for the moving average. Given a time series of data xt, the ARMA model is a tool for understanding and perhaps predicting future values in this series. The model consists of two parts, an autoregressive, which is AR part, and a moving average, that is MA part. The general autoregressive moving average, which is ARMA model, was described in the 1951 thesis of Peter Whittle, Hypothesis Testing in Time Series Analysis, and it was popularized in 1971 book by George E.P. Box and Gwilym Jenkins. The model is usually then referred to as the ARMA P, Q model, where P is the order of the autoregressive part and Q is the order of the moving average part. And the model is written as yt is equal to beta 1 yt minus 1 plus beta 2 yt minus 2 plus so on up to beta p yt minus p plus mu t plus gamma 1 mu t minus 1 plus gamma 2 mu t minus 2 plus so on up to gamma q ut minus q, where the betas beta 1 to beta q are the parameters of the model and the mu t's from mu t to mu t minus q are the white noise error terms. The error terms mu t are generally assumed to be independent and identically distributed, that is IID, random variables sampled from a normal distribution with zero mean and sigma square as the variance, and is generally written as mu t distributed normally n with 0 and sigma square as the variance. These assumptions may be weakened, but doing so will change the properties of the model. In particular, a change to the IID assumption would make a rather fundamental difference. These models are fitted to time series data either to better understand the data or to predict future points in the series, that is for forecasting. They are applied in some cases where data show evidence of non-stationary, where an initial differencing step corresponding to the integrated part of the model can be applied to remove the non-stationarity. This kind of model is generally referred to as an ARIMA P, D, Q model, where parameters P, D and Q are non-negative integers that refer to the order of the autoregressive, integrated and moving average parts of the model respectively. ARIMA models form an important part of the Box-Jenkins approach to time series modeling. When 2 out of the 3 terms P, D, Q are zeros, the model may be referred to based on the non-zero parameter, dropping AR, I or MA from the acronym describing the model. For example, ARIMA 010 is integrated of order 1, which is I1 model, and ARIMA 001 is moving average of order 1, that is MA1. There are certain rules for identifying the order of differencing and the constant of ARIMA models. For example, rule 1 says if the series has positive autocorrelations out to a high number of legs, say 10 or more, then it probably needs a higher order of differencing. Rule 2 says if the lag -1 autocorrelation is 0 or negative, or the autocorrelations are all small and patternless, then the series does not need a higher order of differencing. If the lag -1 autocorrelation is -0.5 or more negative, the series may be over-differenced. Remember, beware of over-differencing. Rule 3 says the optimal order of differencing is often the order of differencing at which the standard deviation is lowest. Not always, though. Slightly too much or slightly too little differencing can also be corrected with AR or MA terms. Rule 4 says a model with no orders of differencing assumes that the original series is stationary, which is it is mean reverting. A model with one order of differencing assumes that the original series has a constant average trend, for example a random walk or simple exponential smoothing model, that is SCS model, with or without growth. A model with two orders of total differencing assumes that the original series has a time varying trend, for example a random trend. Rule 5 says a model with no orders of differencing normally includes a constant term which allows for a non-zero mean value. A model with two orders of total differencing normally does not include a constant term. In a model with one order of total differencing, a constant term should be included if the series has a non-zero
By
average trend.
Peter Whittle in his thesis in 1951 and was later popularized by Box and Jenkins in their book in 1971. They also formulated a method known as Box-Jenkins method to estimate the ARMA models. Now, let us see how the autoregressive moving average model is defined through an equation. Yt is equal to beta 1 Yt minus 1 plus beta 2 Yt minus 2 till beta p Yt minus p plus ut plus gamma 1 ut minus 1 plus gamma 2 ut minus 2 till gamma q ut minus q. This series is a combination of autoregressive model of order p, that is AR of order p, and moving average model of order q, that is MA of order q. Therefore, ARMA model is simply the combination of both AR and MA models.
A spurious relationship is a mathematical relationship in which two events or variables have no direct causal connection, yet it may be wrongly inferred that they do have a statistical relationship because of high value of r square. The reason for this could be either coincidence or the presence of a certain third unseen factor, which is referred to as a common response variable or a confounding factor or lurking variable. Suppose there is found to be a correlation between A and B. Aside from coincidence, there are three possible relationships where A is present, B is observed, which means A causes B. Where B is present, A is observed, that means B causes A. Or where C is present, both A and B are observed, then it means C causes both A and B. In the last case, there is a spurious relationship between A and B. In a regression model where A is regressed on B, but C is actually the true causal factor for A, this misleading choice of independent variable, which is taking B instead of C, is called specification error. Because correlation can arise from the presence of a lurking variable rather than from direct causation, it is often said correlation does not imply causation. A spurious relationship should not be confused with a spurious regression, which refers to a regression that shows significant results due to the presence of a unit root in both variables. The phenomena of spurious regression was first discovered by Yule. He stated that the spurious regression could persist in non-stationary time series even when the sample size taken into consideration is very large. The spurious regression could be judged from the value of Durbin-Watson test, whose d value is extremely low, suggesting a very strong first order autocorrelation. Second method of judging the spurious regression was suggested by Granger and Newbold. They applied a rule of thumb that if r square is greater than d, then the estimated regression is a spurious regression. Therefore, one should be extremely careful while conducting a regression test on a time series phenomena, especially the ones exhibiting the stochastic trends.
It was first discovered by Yule, and according to him, the spurious regression could persist in non-stationary series even when we take the large sample sizes. One of the ways to judge spurious regression is through the Durbin-Watson test. If the value of d is very low, then there is a strong first order autocorrelation and hence spurious regression would occur. A second method of judging the spurious regression was suggested by Granger and Newbold, saying that if r square is greater than d, then the estimated regression is a spurious regression. Therefore, one has to be extremely careful while conducting a regression test on a time series phenomenon, especially the ones exhibiting the stochastic trends. We can summarize the module in the following points. First, a process can be termed as unit root process if the first order autoregressive model becomes equal to 1. Secondly, the integrated stochastic process is explained in detail along with its properties. Thus, we know that any series is said to be integrated of order d if the dth difference is the white noise term. Third, the autoregressive processes are the ones which contain the lagged values of the endogenous or the dependent variables, whereas a moving average process is the one which contains the lagged values of the error term, and thus a regression is carried out on them. Next, we learned that autoregressive moving average, that is ARMA process, is the combination of both autoregressive model and the moving average model. And finally, we studied about the spurious regression and its methods of testing.
Let us now summarize what we have learned in this module. A process can be termed as a unit root process if the first order autoregressive model becomes equal to 1. Autoregressive processes are the ones which contain the lagged values of the endogenous or the dependent variable. For example, yt is equal to beta 1 into yt minus 1 plus beta 2 into yt plus minus 2 plus so on up to beta p into yt minus p plus mu t. A moving average process is the one which contains the lagged values of the error terms and thus a regression is carried out on them. It is the sum of the lagged values of the error terms. For example, yt is equal to mu t plus gamma 1 mu t minus 1 plus gamma 2 mu t minus 2 so on up to gamma q plus mu t minus q. An autoregressive moving average, that is ARMA process, is the combination of both autoregressive model and moving average model. It is defined as follows: yt is equal to beta 1 yt minus 1 plus beta 2 yt minus 2 so on up to beta p yt minus p plus mu t plus gamma 1 mu t minus 1 plus gamma 2 mu t minus 2 so on up to gamma q mu t minus q. Any series is said to be integrated of order d if the dth difference is the white noise. There are two methods of judging this spurious regression. First, when Durbin-Watson value is very low, implying strong first order autocorrelation. And second, when r square is greater than d.